In the previous problem, we solved for the short circuit current when a symmetrical fault occurs in the bus. We accomplished this through network reduction, where we determined the equivalent impedance at this fault point. If we will solve for the short circuit current at other fault locations, let's say here or here, then we need to reduce the network again to determine the equivalent impedance. That is quite easy for a simple circuit like this. But imagine if we have larger networks of 4, 5, or more buses. Solving for the equivalent impedances would be more challenging. This is why we have to introduce this method for fault calculation using the impedance matrix. The network reduction is not efficient and is not applicable to large networks. A more general fault circuit analysis is through nodal method. This is done by utilizing the elements of the bus impedance matrix, the fault current, as well as the bus voltages during fault. Consider a typical bus of an N-bus power system network shown. The system is assumed to be operating under balanced condition and a per-phase circuit model is used. Each machine is represented by a constant voltage source behind proper reactances, which may be X sub D double prime, which is the subtransient reactance, X sub D prime, which is the transient reactance, or X sub D, which is the steady-state reactance. A balanced three-phase fault is to be applied at bus K through a fault impedance Z sub F. The pre-fault bus voltages are obtained from the power flow solution and are represented by the column vector shown. For our notations, N represents the total number of buses present in the power system, and K represents the faulted bus, where the shunt fault point is, where the short circuit occurs. We know that faults cause massive disruption in the electrical system. The changes in the network caused by the fault with impedance Z sub F is equivalent to those caused by the added voltage V sub K of 0 with all other sources short-circuited. And the added voltage may be represented by delta V sub B matrix shown. Zeroing all voltage sources and representing all components and loads by their appropriate impedances, we obtain the Thevenin circuit. From Thevenin's theorem, bus voltages during the fault are obtained by superposition of the pre-fault voltages and the changes in the bus voltage. This equation shows that the voltage in the faulted bus is equal to the pre-fault voltage at the bus plus the change in voltage as the fault occurs. And the injected bus currents are expressed in terms of the bus voltages through this equation. Bus current equals the bus admittance multiplied to bus voltage. This is just the Ohm's law, but with admittance instead of impedance. I bus is the current vector entering the bus, and Y bus is the admittance matrix. The impedance matrix is used to determine the equivalent impedance if a fault were occur to any bus in the system. But the only way to find impedance matrix is to formulate admittance matrix for the system and find its inverse. So let's determine how we can set up the admittance matrix. Let's try setting up the admittance matrix for this 3-bus system. Its admittance should have 3 rows and 3 columns since we have a 3-bus system. The diagonal element of each bus is the sum of the admittances connected to the individual buses. For Y11 element, the admittances connected to it are YG1, YG2, and YT. For the Y22 element, the admittances directly connected to bus 2 are YT and YL. And for Y33 element, only YL is directly connected to bus 3. While the off-diagonal elements are equal to the negative of the admittance between buses. Y12 is equal to Y21, and this is equal to the negative of the admittance value that is directly between buses 1 and 2. Between buses 1 and 2, there is the transformer admittance. So they are equal to negative Y sub t. Y13 is equal to Y31. Since there is no admittance directly linking buses 1 and 3, they are equal to 0. And Y23 is equal to Y32. Between buses 2 and 3, there is the transmission line admittance. So they are equal to negative Y sub L. With that, we have completed the 3x3 admittance matrix, 3 diagonal elements and 6 non-diagonal elements. In the Thevenin circuit, current entering every bus is 0 except at the faulted bus. Since the current at faulted bus is leaving the bus, it is taken as negative current entering bus K. Thus, the nodal equation to the Thevenin circuit becomes this in matrix form. Or this can be simplified into this equation. The fault current injected into the bus is equal to the admittance matrix multiplied to the matrix for change in voltage during fault per bus. Taking the previous equation, let's rewrite it solving for the change in bus voltage matrix, where the impedance matrix is equal to the inverse of the admittance matrix. From the equation for bus voltage during fault that we have shown earlier, where change in bus voltage at fault is equal to the impedance matrix multiplied to the injected bus current at fault, replacing the change in bus voltage at fault, and we have this matrix equivalent to this equation. Since we only have one single non-zero element in the current vector, and that is at the negative I sub k row, then we will have this equation. From the Thevenin circuit, we have this equation. This is basically just an application of Ohm's law during fault condition, after the entire circuit was simplified into its equivalent. In this analysis, we will also assume that the fault voltage at the fault point is 0. We will have this equation to solve for the short circuit current at fault point bus K. For a bolted fault, this means that the fault impedance is assumed to be 0. Then this will be our working equation for short circuit current at fault point bus K. So what does this imply? For a fault at bus K, we only need the ZKK element of the bus impedance matrix and the pre-fault voltage. So if we already have the impedance matrix, we can easily solve for the short circuit current at any bus of the power system. If you are looking for the short circuit current at bus 1, it is equal to the pre-fault voltage at bus 1 over Z11 element of the matrix. Replace the denominator with Z22 for short circuit current at bus 2, and so on. Also, writing the equation in terms of its element Refer to this equation in matrix form that we have shown earlier. Simplifying it, we will have this equation. Substituting for I sub k at fault, bus voltage during the fault bus I becomes this. This will be our working equation in solving for the voltage at any bus I during the occurrence of fault at bus K. With the knowledge of bus voltages during fault, we can calculate the fault current in all lines, define positive in the direction I to J. So with the knowledge of the bus impedance matrix, the fault current and bus voltages during the fault are readily obtained for any faulted bus in the network. Only way to find impedance matrix Z bus is to formulate the admittance matrix Y bus for the system and find its inverse.